we are going to, I'm going to do it, but you're going to watch, you're going to participate. Determine the magnetic field due to a loop of wire along an axis of the wire. Two ways I'm going to do this. I'm going to do this the normal calculus way, and then we're going to do it with Python. And I think both of those ways kind of help us visualize what's going on. So I have here a loop in the XY plane with a current, and the current's coming this way, right? So just a reminder, a dot like that means that the vector for the current times the length is coming this way. And then an X means a current or vector going that way. Okay, that's just that's one way we draw these things. So up here, I have the current coming out of the page at the top. So it's going in at the bottom. Now we have the law of Biot and Savart for magnetic fields due to short wires. So if I have a tiny little segment of wire, I delta L vector, and I want to find the magnetic field over here, a vector R away, then we use this. The magnetic field due to this piece, mu naught over 4 pi, that's a constant. I delta L cross R, that's the cross product divided by the magnitude of R cubed. Okay, so don't worry, we're going to review cross product and stuff like that, but let's just get to this problem. So let's break this into pieces right here. I'm going to break that into a tiny little piece. And so I want to find the vector location of the observation location and the vector location of the piece. I'm going to call it R cubed because I did that before. That's the way I do it with other things. So let's write this out as RO. The vector location of my observation location is going to be 0, 0, Z, right? And then my vector location of my charge, RQ, is this. So that's going to be 0 in the X direction, R in the Y direction, 0 in the Z direction. And I need that so I can find R, the vector from here to there. R is going to be RO minus RQ, so that's going to be equal to 0 minus RZ. Got it. Okay, so that R is this R. Now, I need I delta L. Okay, so that's not easy here because as we move around the loop, I delta L changes. So we're going to use a trick. Trick alert. I don't like tricks, but sometimes you got to use a trick. So there's a trick. Not a super big trick. And it makes sense at the end. We're going to invoke symmetry. So up here, if I have this current coming out of the paper like that, okay, what direction would that be in? That's actually in the negative X direction, right? Because if this is my Y direction and that's Z, then X would be into the paper, right? Because we have to have X cross Y is equal to the Z direction. So it's not, this is not X. So that's X. So this is coming in the negative X direction. So I'm going to write I delta L for that top piece as negative I dl 0, 0. So it's in the negative X direction. How's that? Okay. Now I'm going to need two things. I'm going to need the magnitude of R down here. I'm going to go ahead and find that. And then I need to find this I delta L cross R. So let's do the magnitude of R. That's not too hard. The magnitude of R is going to be the magnitude of this. So it's going to be this squared plus this squared square rooted. So I get the square root of R squared plus Z squared. So that's just the magnitude of that. Now what about the cross product? We do have to do this, okay? So let's do I delta L cross R. So one of the ways to do the cross product, you can look up the formula, but I always just like to write this down. It's the determinant of the matrix X hat, Y hat, Z hat. And then I need to put the X components of I delta L right here, negative I dl 0, 0. And then the components of R, which is 0, negative R, Z. Now, when I take the cross product, I'm going to expand about the top row. So if I do that, I need to take the determinant of this matrix. So it's 0 times Z minus 0 times negative R, so that's 0. Now we're going to do the Y. For the Y, remember that there's a negative sign associated with it. So we're actually going to do this 0 times 0 minus this times this. So I actually get minus times minus is a positive, but then there's a minus. So I get minus I dl R. And then finally, my Z component, it's going to be this times that, which is I dl r. Okay, so I have the magnitude, I have the cross product. Let's put it into this equation right there. Piece of paper. Okay, so I'm going to put this right here. Delta B, that's just the magnetic field just due to this piece right here. Mu naught over 4 pi, I'm going to write it out. I delta L cross R divided by the magnitude of R cubed. Okay, so that's that. So I'm going to write mu naught over 4 pi. And then I'm going to hold this off because it's a vector. I'm just going to put 1 over this cubed. So that's going to be r squared plus z squared, square rooted cubed, which is to the 3/2. And then I have this vector, 0, negative I dl r, I, no, that's z. Because that was this, yeah? Okay, so z. Z. I dl r. Right? So let's see. The y component, I cross that out. Z. Yeah. Okay. Now, what do we do? Well, I don't want to integrate around the loop because this is hard to change, right? This IDL changes, and it's possible to do it. But now we're going to use that trick, right? So if I draw the loop from the side, there's my current. There's my loop. And there's my current. So I want to now do the same thing for this piece down here. So let's do the whole thing again. The only thing that's different is the location of the piece and the direction of the current. So now I have RQ is equal to the vector 0, negative R0, and I delta L is going to be into the positive x direction. So it's I dl 0, 0. So this changes my vector r. It's going to be positive r. So r is going to be equal to the vector 0, r, z. And then I need to redo I delta L cross r. So let's do that. And this time we won't make a mistake. Cross r is going to be x hat, y hat, z hat. You got to say these things out loud or you're going to make a mistake. And then I'm going to put my I vector, I delta L vector, that's right, I dl 0, 0, and then my r vector 0, r, z equals. And so we're going to get the x component is going to be 0. The y component is going to be this minus that. So I minus that one should be positive because it's, wait, this times that minus a negative, no, this times that, z, so this should actually be positive. Making mistakes here, making mistakes. And I'm not going to stop and go back because, like, hey, I can just redo the video. Not going to do that. Mistakes are part of life, right? It's catching the mistakes that are fun. So if you dropped out before I caught that mistake, that's fine. So this is plus. But this is going to be minus I dl z, right? Because I'm going to get this minus that. So I get a minus. And then for the z component, I get positive I dl r. And I can write this is dB1 delta B2 on the bottom is going to be equal to the exact same thing except for mu naught over 4 pi 1 over r squared plus z squared to the 3/2. That's the same, right? Because it's the magnitude the same. But then my vector here is 0 minus I dlz I dlr. Now when I add these two together, notice what happens. 0 plus 0 is 0. Negative I dlz plus I dlz is 0. IDLR plus IDLR is 2. So the only surviving component from those two pieces right there is going to be in the z direction. And that's going to be true for all the pieces. As I add up around here, the only piece that will survive will be the z direction, and I get 2 of them. So that's kind of a trick, but that's what I have. So let's write out our magnetic field after the trick. I'm going to put after trick. And I can't even spell that. So delta B is going to be mu naught over 4 pi 1 over r squared plus z squared to the 3 halves. And then I have 0, 0, 2I dlr. So the only vector is going to be in the z direction. Okay. A lot of times you can draw that. A lot of people draw that right here. If I have a magnetic field coming out of the board, it's going to be dB is that way. Into the board, dB is going to be this way, and those two components in that direction cancel. The only thing you get is in that direction. But we did that by writing it out, right? We didn't have to draw that. So let's write dBz. I'm going to write it as dB because I'm going to integrate. dBz is mu naught over 4 pi 1 over r squared plus z squared to the 3 halves, and then I have that 2I r dl. And as I go around the loop, mu naught over 4 pi doesn't change. 1 doesn't change. 2 doesn't change. I doesn't change. R doesn't change. None of those things change except dl. So I actually can integrate this and just say bz is, I'm going to pull out everything, mu naught over 4 pi 2I r over r squared plus z squared to the 3 halves, the integral of dl. So if I integrate this over dl, and I feel like I'm getting an extra 2 in there, but that's fine. I'm just going to get L, the length of the circle, right? So if I have a circle with the radius r, L, or let's write it as the integral of dl is going to be L, which is 2 pi r. So this is just 2 pi r. So bz is mu naught over 4 pi 2I r over r squared plus z squared to the 3 halves times 2 pi r. And let's just simplify that. I get mu naught over, I have a 2 there, shouldn't have, over 4 pi Oh, I don't get the 2. Okay. There's not a 2 there. Because, yes, once I add these two pieces, but when I'm integrating, the only thing that survives is that. So this is not going to have a 2 there. That's not going to be a 2. That's not going to be a 2. That's not going to be a 2. Okay. Sorry. I'm making a lot of mistakes. Usually I work these things out beforehand and I don't make mistakes. Okay. So I get I times 2 pi r squared over r squared plus z squared to the 3 halves. And that's bz. Done. Okay, now let's look at the limit as z gets really large. If z is much greater than r, then this becomes bz is approximately equal to mu naught over 4 pi. I still get the 2 pi r squared times I. Now this on the bottom, if z is very large, I'm going to get z squared, and that's tiny, so I just get z cubed. And this looks like, if you remember, the electric field due to a dipole, E on the axis was 1 over 4 pi epsilon naught 2qs over r cubed. This looks the same thing, right? We have a constant over r cubed. We even get the 2 there. So we can write this as mu naught over 4 pi mu over r cubed. where mu is equal to I times A. No. Yeah, 2 mu. So that's the area of the circle, pi r squared, and that's I. Okay. So that took a while. But of course, what we want to do now is to do this in Python. And I think doing it in Python can help us see a lot of stuff. Okay. So if we want to do this in Python, we're going to have to break it into numbers. So we're going to have to pick the size of the circle and an actual current. But let's just get right to it, because there's a lot of work we have to do, because there's some tricky stuff here. So I'm switching to Python. This is Python. Of course, I'm going to give you the code afterwards. And of course, I'm going to make this much bigger, because you can't see that. I have a 1 there just so I could save it. Okay, let's start off with our constants. I'm going to call the constant, the mu naught over 4 pi, I'm going to call Km. Km is 1 times 10 to the negative 7th. That's just our constant value. The radius of the circle, let's go with, it doesn't really matter, 0.01, and then the current of 1 amp. And I'm going to need that location z. So let's just start off with z equals 0.01. So the same as the radius. I need to define my observation location. I need to also create my ring of current, and that's going to be the problem. Creating a ring of current is going to be difficult. I can create a ring of charges, but a ring of current is not so easy. And so, and just so we can see it from the side, I'm going to make my ring in the YZ plane, and I'm going to put my observation location on the x-axis, just so I'll orient it correctly in terms of WebVPython, but we'll get the same thing in the end. So let's go ahead and put our, let's call this actually x in. Let's put our observation location as just a vector. I'm not even going to draw it. Vector 0, x0, 0. And now I want to make my ring. So how do I make a ring? Let's just put some points there, okay? So I'm going to break this into n equals 10 pieces, and I'm going to have a theta value. My theta value is going to move around in a circle. Maybe I should draw this picture. Yeah, let's draw the picture real quick. So I'm going to do it this way. So this is going to be y, z, let's just pick. And it has a radius r. So each piece is going to be defined by its angle theta. So RQ is going to be equal to the x component 0. The y component is going to be r cosine theta. The z component is going to be r sine theta. And then theta is just going to be theta plus d theta, where d theta is equal to 2 pi over n. So I can increase my value that way and move around the circle. Does that make sense? Oh, actually, my y component is going to be in the sine, because this is going to be my z. So I'm going to switch those up. Okay, back to the computer. So I need theta. Theta. 0. D theta is equal to 2 times pi divided by n. And now I can just say while theta is less than 2 times pi, do the following. Number 1, I'm just going to create that vector. RT equals vector 0 r times sine theta, r times cosine theta. Is that right? Yep. Okay, so that's my temporary vector. Now with that temporary vector, I'm going to put a sphere there, and then we can just see what it looks like. Sphere position equals RT, radius equals R over 20. I don't even know, I'm picking that. Now I'm going to increase my value of the angle. Theta equals theta plus d theta. And let's run that. I should get 10 spheres in a circle. Whenever it takes a while to run like this, I'm thinking I made a mistake. Ugh. Did I really make a mistake? It's not loading. The whole thing crashed. Wow. Okay, it did. It worked. It was just slow. There it goes. So, ha! Whew. Okay. So there's my 10 spheres in a circle. And I don't want spheres. I want vectors. I want IDLs, right? That's what I want. So I need to, at each of those points, create an delta L. That's going to be kind of tough, right? Because they're all in different directions. But I need those directions numerically. So we're going to use the cross product. Let me go back over to the paper and show you why. So suppose I have a circle. And I can find the vector location of each one of those pieces with the vector RQ. That's what I have it as RT. And I want to make this vector that way. I'll call that DL. Well, the first thing I can do is to find the length of this. I'll call it DS. It's just going to be 2 pi r over n, right? Because each length of this piece is going to be a part of the total circle around there. And then I can say DL is going to be the cross product of, it's going to be x hat cross r hat. And then multiply that by ds. So remember that the cross product, we use the right-hand rule. So if I have this as the r hat direction, this is my x direction coming out of the paper, and if I do x cross r using the right-hand rule, I get that direction. So that shows me the correct direction by using x hat and r hat. So let's go ahead and make our x hat vector, which we could call it something else, but I'm gonna make it. Up here I'm gonna say x hat is equal to the vector 1, 0, 0. I need ds. ds is going to be 2 times pi times r over n, right? That's how long each piece is. And then down here, I can make my dl. dl is going to be equal to ds times cross x hat norm rt, right? So norm, I have to do that norm rt because I don't want the r in there, although it would still work. You could just fix it with ds. But I have, gives me just a direction. That's just a direction. And that's my length, and that's my DL vector. Now, what I want to do is to draw that. So let's draw that with an arrow. The position is going to be equal to RT, and the axis is going to be equal to DL. So let's see what that looks like. So there I have 10 vectors. And each one of those vectors at that point points in the direction of the I delta L. So I have all my I delta L vectors. Yeah, and they're not perfect, and it's not perfect for sure. But it works, right? So wherever I go in the circle, I can get that I delta L vector. I need that, and it looks cool too. So we got that going for us. Now we can just calculate the magnetic field. That's all we really needed. So down here, I'm going to say B equals vector 0, 0, 0. And then down here, I don't actually even need those things, but that's fine. I need to, 1, calculate R, 2, plug into my Booleans of R equation. So I have RT, I can calculate R. R is going to be equal to RO minus RT, right? Because that's the observation location minus the vector position. And let's go ahead and calculate dB. dB is Km, which is mu naught over 4 pi, mu naught, yeah, and then times the cross product of I times dl, right? That's, and the other vector is r. And then you divide by the magnitude of r cubed. That's it. That's the magnetic field due to each one of those little pieces. Now I can just add it to the total. B equals B plus dB, and I'm done. So down here, let's print B equals B, and the units be Tesla. And let's see if this runs, and then we can calculate the theoretical version and see how that compares. So there's that. It's -0 in the y and z direction, right? Because it's super tiny, and it is in the x direction, which is on the axis of the plane, just like we said. So over here, let's calculate the theoretical bt. I'm going to look at my equation, which I covered up. Where did it go? There it is. It's going to be equal to mu naught over 4 pi, so km times I times 2 times pi times r squared divided by R, capital R, squared, plus x, I'm using x here, squared, raised to the 3/2. And let's print that. BT equals B Tesla. Run it. Oops, what happened? Oh, I clicked the wrong button. Run it. Okay. Oh, I printed B. I didn't print BT. I was like, it's exactly the same. And it's a vector, and I didn't even calculate the vector. This is BT. So right there, very, very close. That's with n equals 10 pieces. I only broke it into 10 pieces. Okay. So it works. So that's that. Now, of course, the next thing is going to be able to build a model to visualize the magnetic field due to a loop at any different place. Because the nice thing about this code is I put the observation location on the x-axis, but I can put it anywhere. It doesn't matter where it is, right? I'm calculating the magnetic field due to each one of those pieces, and I can just, it doesn't matter that it's on the axis or not. Okay, so made a couple errors, powered through. I think it's all good in the end. Put a link to the code down below. Hope you find this useful. Talk to you later.